Bismillahirrahmanirrahim. Today's in our lecture, we will study chapter 7, combustion. Before chapter 7, in chapter 6, we have studied the air and fuel mixture which is entering inside the combustion chamber. Now, in this chapter, we will study what is happening inside the combustion chamber or cylinder. Now, we can divide combustion into three broad regions for an SI engine. First one is the ignition and the flame development. Second is the flame propagation. Third part, the last part, is the flame termination. Now we are talking about the combustion with respect to SI engine. So the combustion is divided into three broad regions. First one is the ignition and the flame development. Second is the flame propagation. Third is the flame termination. Now combustion in SI engine. Flame ignition and development is generally considered the consumption of the first 5% of the air-fuel mixture, or 5 to 10% in some book it says that. During the flame development period, ignition occurs and the combustion process starts, but very little pressure rise is noticeable and little or no useful work is produced. Just about all useful work produced in an engine cycle is the result of the flame propagation period. So in flame ignition and development, very small pressure rise and no noticeable useful work. But all the useful work that is produced during the engine cycle is in the flame propagation period of the combustion process. This is the period when the bulk of the fuel and air mass is burned, means 80 to 90% of the fuel mass is burned. During this time, pressure in the cylinder is greatly increased, and this provides the force to produce work in an expansion stroke. Now, the final 5%, which is left after the flame ignition and development and flame propagation, the leftover the 5%, of the air fuel mass which burns is classified as flame termination. During this time, pressure quickly decreases and combustion stops because due to increase in the volume of the combustion area. In an SI engine, combustion ideally consists of an exothermic subsonic flame progressing through a pre-mixed homogeneous air-fuel mixture. So in an SI engine, combustion ideally consists of an exothermic subsonic flame progressing through the pre-mixed homogeneous, not heterogeneous, homogeneous air-fuel mixture. The spread of the flame front is greatly increased by induced turbulence. The spread of the flame front means the propagation of the flame front is greatly increased by inducing the turbulence, swirl, and squish within the cylinder. The right combination of fuel and operating characteristic is such that knock is avoided or almost avoided. So you should have a right combination of air-fuel mixture and the operating characteristics in a such a way to avoid the knock. Now let's see figure 7-1. Cylinder pressure in the combustion chamber of an SI engine as a function of crank angle. Now, the increase in the pressure rise is very slow after ignition during the flame development period. This results in a slow pressure force increasing on the piston and smooth engine cycle. Maximum pressure occurs 5 to 10 degree after TDC. Now on x-axis, we have crank angle in degrees, and on y-axis, we have pressure. Now, your piston is at BDC, your compression stroke is starting. When piston is now moving from BDC to TDC in your compression stroke. Somewhere here, before the TDC, you get your spark plug ignites and it gives the ignitions to that compressed air fuel mixture. So there is very small rise in pressure till the piston reaches the top dead center. So this portion at the top dead center, on the left side, we have a negative work or very less or negligible work. Okay. Then after the ignition, flame propagation develop. So we have a maximum pressure and maximum temperature at this degree, and the maximum pressure we achieve in a combustion cycle, that is at 5 to 10 degree after TDC. Now at TDC, your compression stroke finishes and your power stroke starts, and we already got the ignition, the combustion started. We got the maximum temperature and pressure when the piston reached at 5 degree to 10 degree after TDC. Now piston is moving towards BDC. Somewhere here, your exhaust valves open, so you have an exhaust blow down. So pressure is dropping quickly. Okay. So this is how the pressure versus crank angle in your combustion cycle. Now ignition, let's talk one by one all the three broader regions of the combustion. Ignition and flame development, the first part. The combustion is initiated by an electrical discharge across the electrodes of a spark plug 10 to 30 degree before TDC. So our combustion is initiated by an electrical discharge across the electrodes of a spark plug that is 10 to 30 degree before TDC. We get this is the range in which we get the spark, and then we get the initiation of the flame. This high temperature plasma discharge between the electrodes ignites the air fuel mixture. So this high temperature plasma discharge between the electrodes ignites the air fuel mixture in the immediate vicinity, and the combustion reaction spreads outward from there. So ignition creates a spherical frame. So flame is in spherical shape. Remember this thing. Ignition creates a spherical frame front that propagates outward in the combustion chamber. It does not generate enough energy to quickly heat the surrounding gases and thus propagates very slowly. So at the start of the flame front propagation, the spherical flame develops, but that does not propagate very quickly because of the surrounding losses. The combustion starts very slowly because of high heat losses to the relatively cold spark plug and gas mixture at that time. So flame can generally be detected at about 6 degree of crank rotation after the spark plug. So you got the ignition, but that flame is detected after the 6 degree of crank rotation. Let's suppose you get the ignition 10 degree before TDC. So at 170 degree, you get the spark plug ignition. Now, after 6 degree of crank rotation, that flame is generally visible. So at 176 degree of the crankshaft angle, this spark flame can be detected. But in example 7-1, the author has given after 8 degree of crank rotation. So we'll take the 8 degree of crank rotation that the flame is detected there. So generally it is after 6 degree the flame is detected. When a spark plug fires, the plasma discharge ignites the air fuel mixture between and near the electrode. This creates a spherical flame front that propagates outward into the combustion chamber. At first, the flame front moves very slowly because of its small original size. It does not generate enough energy to quickly heat the surrounding gases and thus propagates very slowly. This in turn does not raise the cylinder pressure very quickly, and very little compression heating is experienced. For example, at the end of the compression stroke, if we have a large amount of pressure which is exerting on the piston, then it will be difficult for the pistons to complete its upward movement. So that's why it propagates very slowly and very near to the TDC. When after TDC, 5 to 10 degree after TDC, the combustion fully develops and it propagation and flame is propagated fully. So we get the maximum temperature and pressure that is exerting on the piston top. So piston is forced fully move downward. So all the forces are acting on the piston face. So it is going down in a speed. Okay. No, ignition only after the first 5 to 10% of the air fuel mass is burned does the flame velocity reaches higher value with the corresponding fast rise in the pressure, the flame propagation region. It is desirable to have a rich air-fuel mixture around the electrodes of the spark plug at ignition. So one thing or one aspect is that it is desirable to have a rich air-fuel mixture around the electrodes of the spark plug at ignition. A rich mixture ignites more readily, has a faster flame speed, and gives a better start to combustion, the overall process. Spark plugs are generally located near the intake valves to assure rich mixture, especially when starting a cold engine. So remember this thing. Spark plugs are generally located near the intake valves. So they are not placed in exactly in the center. They are placed towards the intake valves to assure a rich mixture, especially when starting a cold engine. Now, applied potential is generally 25,000 to 40,000 volts with a maximum current on the order of 200 amperes lasting about 10 raised to power minus 9 seconds, means nanoseconds. Okay, so the volts applied across the electrodes are 25,000 to 40,000 volt with a maximum current on the order of 200 ampere. And this current is now question arises in generally in our vehicle we have 12-volt battery. So how this much of a current and voltage can be achieved? So it is due to the HT coil, high tension coil. If you remember the simple flow diagram in the electric circuit, the current from the battery, the ignition switch is coming to the distributor cap, from this distributor cap, ignition coil to the distributor cap. After that, ignition coil is producing this much of a volts and ampere, and that spark is lasting about 10 is from 9 minus 9 nanoseconds. This gives a peak temperature on the order of 60,000 Kelvin. So for this much of a time period, we are achieving peak temperature of the order of 60,000 Kelvin. Overall spark discharge lasts about 0.001 second. So the spark discharge from that spark plug is of time frame 0.001 second with an average temperature of about 6,000 Kelvin. A stoichiometric mixture of hydrocarbon fuel requires about zero point 0.2 millijoules of energy to ignite self-sustaining combustion. So when we have a stoichiometric mixture of hydrocarbon fuel, means the quantity of the fuel and the air is in stoichiometric ratio, we only require 0.2 millijoules of energy to ignite self-sustaining combustion. This varies to as much as 3 millijoules for non-stoichiometric mixture. So if we have a non-stoichiometric mixture, this energy required is 3 millijoules for self-sustaining combustion. The discharge of a spark plug delivers 30 to 50 millijoules. So it is much more than the required one, 0.2 to 3 millijoules. So it gives us 30 to 50 millijoules of energy, most of which, however, is lost by the heat transfer. So we only require 0.2 to 3 millijoules from stoichiometric mixture to non-stoichiometric mixture for their self-sustaining combustion ignition. But the spark plug is discharging 30 to 50 millijoules of energy, most of which, however, is lost by heat transfer. So, summary of the important event which is happening in the ignition and flame development, initiated by an electrical discharge slightly before TDC, ignites the air-fuel mixture in the immediate vicinity, create a spherical flame front which travels outward very slowly. Flame can generally be detected at about 6 degrees of crank rotation. After the first 5 to 10% of the burnt air fuel mass, flame velocity reaches higher value. Desirable to have a rich air fuel mixture around the electrodes. Discharge of a spark plug delivers 30 to 50 millijoules of energy. So this is the first portion of the combustion, ignition and flame development. Now, a few words regarding the spark plug electrode gaps. The gap distance between the electrodes on a modern spark plug is about 0.7 to 1.7 mm. So the gap between the electrodes on a modern spark plug is 0.7 to 1.7 mm. How we can measure this gap? So with the help of a feeler gauge, we can measure this gap from zero point 0.7 to 1.7. Feeler gauge, basically a gauge with the different variable metal strips of different thickness, with the help of which we can check the gap. Smaller gaps are acceptable if there is a rich air-fuel mixture or if the pressure is high. If on the smaller side means zero point 0.7, smaller gaps are acceptable. The condition is this: if there is a rich air-fuel mixture or if the pressure is high, high inlet pressure by turbocharging or high compression ratio. Normal steady state temperature of a spark plug electrodes between firing should be about 650 to 700 degrees Celsius. A temperature above 950 degrees Celsius risks the possibility of causing surface ignition. And we know that if there is a surface ignition temperature uh, and we get the knock. The temperature above 950 degrees Celsius risks the possibility of causing surface ignition, and the temperature below 350 degrees Celsius tends to promote surface fouling over extended time. So if we have a temperature above 950, we have the possibility of self-ignition temperature. And if we have the temperature below 350 degrees Celsius, then we have another problem, that is surface fouling over extended times. Fouling is basically the deposition of layer on the surface. For older engines with worn piston rings that burns an excess of oil, hotter plugs are recommended to avoid fouling. So to avoid that metal deposition on the walls or on the plug, so hotter plugs are recommended if we have a worn piston ring that burns excess of oil. The temperature of a spark plug is controlled by the heat loss path manufactured in the plug. So we have to design that heat loss path manufactured into the plug. Hotter plugs have greater heat conduction resistance than do colder plugs. Modern spark plugs are made with better, more expensive material and have a much greater lifespan than those of a decade ago. Some quality spark plugs with platinum tipped electrodes are made to last 160,000 kilometers or 100,000 miles or more. So modern spark plug with better are made with better and more expensive material, have much greater lifespan than those of decade ago, the old techniques. Some quality spark plugs with platinum tipped electrodes are made to last 160,000 kilometers or 100,000 miles or so. Now, the second part of the combustion, that is the flame propagation in an SI engine. By the time the first 5 to 10% of the air fuel mass has been burned, the combustion process is well established and the flame front moves very quickly through the combustion chamber. So in flame ignition and development, the 5 to 10% of the air fuel mass has been burned. After that 5 to 10% of the fuel mass has been burned, the flame propagation has been developed very quickly and moves in the combustion chamber. Due to induced turbulence, swirl and squish, flame propagation speed is about 10 times faster than if there were a laminar flame front moving through the stationary gas mixture. So due to this induced turbulence, swirl and squish, flame propagation speed is 10 times faster. 10 times faster if we have a same thing in the laminar flame front moving through a stationary gas mixture. In addition, the flame front, which would expand spherically from the spark plug in a stationary air, is greatly distorted and spread by these motion. So in addition, the flame front, which would expand spherically from the spark plug in stationary air, is greatly distorted and spread by these motions. As the gas mixture burns, the temperature and consequently the pressure rises to high values. Burned gases behind the flame front are hotter than the unburned gases before the flame front, with all gases at about the same pressure. So the pressure behind the flame front is more as compared to in front of them. So they will be pushing the flame front in towards the unburned fuel. Now, this decreases the density of the burned gases and expands them to occupy a greater percent of the total combustion chamber volume. So hotter the gas is, lesser the density is, and it will expand to occupy a greater percent of the total combustion chamber volume. A temperature rise from radiation then further raises the pressure. So a temperature is rising with convection, convection, and radiation, but the majority of the temperature rises from the radiation. Heat transfer by the conduction and convection are minor compared with radiation due to the very short real time involved in each cycle. So all the mode of heat transfer are there, conduction, convection, and radiation. But radiation, heat transfer by the radiation is more as compared to the conduction and convection in the combustion chamber. As the flame moves through the combustion chamber, it travels through an environment that is progressively increasing in temperature and pressure. As the flame moves through the combustion chamber, it travels through an environment that is progressively increasing in temperature and pressure. This causes the chemical reaction time to decrease and the flame front speed to increase at a desirable results. Now, because of the radiation, the temperature of the unburned gases behind the flame front continue to increase, reaching a maximum at the end of the combustion process. Temperature of the burned gases is not uniform throughout the combustion chamber. Remember this thing. This temperature increase is not uniform. So temperature of burned gases is not uniform throughout the combustion chamber, but is higher near the spark plug where the combustion started. This is because the gas here has experienced a greater amount of radiation energy input from later flame reaction. Now, ideally, the air-fuel mixture should be about 2/3 burned at TDC. Now, when your piston reached at TDC, ideally the air-fuel mixture should be 2/3 be consumed and almost completely burned at about 15 degree after TDC. So maximum pressure and temperature we achieve 5 to 10 degree after TDC, and the fuel should be completely burned 15 degree after TDC. This causes maximum temperature and pressure of the cell cycle to occur somewhere between 5 degree to and 10 degree after TDC, about optimum for 4-stroke cycle SI engine. Now, comparison of burn mass volume versus volume in combustion chamber of an SI engine. Now, first see the graph. On x-axis, we have percent of volume burned from 0 to 100% and percent of mass burned from 0 to 100%. Now, when only 30% of the gas mass is burned, now when 30% of the gas mass is burned, the burned gases already occupy almost 60% of total volume. Now see, this is your 30%. So it is almost occupying the 60% volume of that chamber. No, compressing 70% of the mixture that is not yet burned into 40% of the total volume. So this 40% volume is available for the burning of 70% by mass. In first portion, 30% of the gas mass is burned and occupy the 60% volume space. No, 70% of the mass is left and that will burn in the 40% of the volume space. Comparison. Now, comparison of the unburned gases raises their compression of the unburned gases raises their temperature by compressive heating. In addition, radiation heating emitted from the flame reaction zone, which is at a temperature on the order of 3000 Kelvin, further heats the gases in the combustion chamber, unburned and burned. Now, average flame speed. Average flame speed in the combustion chamber of an SI engine as a function of air-fuel ratio for gasoline type fuel. On x-axis, we have air-fuel ratio, and on y-axis, we have flame speed. Now, we know the compression ratio is 15 to 1. On our left side, we have a rich mixture. On the right side of this, we have a lean mixture. Initially, in this rich area, the flame speed increase, but as we go to the lean area, it decreases. Lean air fuel mixtures have slower flame speed with maximum speed occurring when slightly rich at equivalence ratio near 1.2. So when we have an equivalence ratio of 1.2, we have a maximum speed of that flame front. Now, average combustion chamber flame speed of an SI engine as a function of engine speed. On x-axis, we have engine speed in RPM. On y-axis, we have flame speed in meters per second. More the speed is, more the flame speed is. As the engine speed increases, the intensity of the turbulence, swirl, squish, and tumble all increases, resulting in a faster flame speed. So more the engine speed, more the intensity of the turbulence, swirl, squish, and tumble, all these increases resulting in a faster flame speed. Now, burn angle. The typical burn angle, the angle through which the crankshaft turns during the combustion is about 25 degrees for most engines. Okay, so it is 25 degrees for most engines. If the combustion is to be completed at 15 degrees after TDC, then ignition should occur at about 20 degrees before TDC. So I read again the typical burn angle, the angle through which the crankshaft turns during the combustion is about 25 for most engines. If the combustion is to be completed at 15 degrees after TDC, so then ignition should occur at about 20 degrees before TDC. If ignition is too early, the cylinder pressure will increase to undesirable level before TDC. and the work will be wasted in the compression stroke. If ignition is late, peak pressure will not occur early enough and the work will be lost at the start of the power stroke due to lower pressure. Actual ignition timing is typically anywhere from 10 to 30 degree before TDC. So the actual timing is somewhere between 10 to 30 degree before TDC. So 30 degree before TDC means if we starting from BDC 0 and TDC is 180 degree, so it is somewhere 150 degree depending upon the fuel used, engine geometry and engine speed. So actual ignition timing is typically in the range of 10 to 30 degree before TDC, depending on the fuel used, engine geometry and engine speed. For any given engine, combustion occurs faster at higher engine speed. Now burn angle. Burn angle as a function of engine speed for a typical modern SI engine with fast burn combustion chamber. Burn angle is the angle through which the crankshaft turns during the combustion. The increase in the angle of the ignition and flame development period, 5% burn, is mainly due to the almost constant real time of the spark ignition process. During flame propagation, 5% burn to 95% burn, both combustion speed and the engine speed increases, resulting in a fairly constant burn angle of about 25 for the main parts of the combustion. So this on x-axis we have an engine speed, on y-axis we have burn angle, degree of crankshaft rotation. So this is 5% burn and this is 95% burn. So during the flame propagation, 5% burn to 95% burn, both combustion speed and engine speed increases, resulting in a fairly constant burn angle of about 25 degree for both main parts of combustion. Now, flame propagation in modern engines automatically adjust ignition timing with electronic control. In our latest engine, the modern engines, due to ECU engine control unit or the computer and sensors which are available in the modern engines, it automatically adjusts the ignition timings with electronic controls. These not only use engine speed to set timings, but also sense and make fine adjustment for knock and incorrect exhaust emissions. So as we have studied different types of sensors in chapter 5, the sensors gives the input to the ECU. From there, all the input is coming regarding the engine speed, regarding the exhaust, regarding the oxygen, regarding everything. So emissions. So this will automatically adjust the ignition timings. Old engine or earlier engine used a mechanical timing adjustment system that consisted of a spring-loaded ignition distributor that changes with the engine speed due to centrifugal forces. In old engines or earlier engine, we used a mechanical timing adjustment system that consisted of a spring-loaded ignition distributor that changes with the engine speed due to centrifugal forces. Now at pot throttle, ignition timing is advanced to compensate for the resulting slower flame speed. At pot throttle condition, the ignition timing is advanced to compensate for the resulting slower flame speed. Ignition timing on many small engine is set at an average position with no adjustment possible. Some in small engines or in where we do not have that modern delicate equipment, the sensors, the ECU, the ignition timing is adjusted as an average position with no adjustment possible. Now the last part of the combustion, the flame termination. At about 15 degree to 20 degree after TDC, 90 to 95% of the air fuel mass has been combusted and the flame front has reached the extreme corners of the combustion chamber. So when piston is at TDC 0 degree, so moving now after 20 degree, we have a more volume. So the air fuel mass has been combusted and the flame front has reached the extreme corner of the combustion chamber. The last mass of the air and fuel will react in a very small volume in the corners of the combustion chamber and along the chamber's walls, slowing down end gas reaction. Because on the wall we have a viscous drag and so many other factors, the area is more, volume has increased, and on wall we have a thin film of oil, lubricating oil, so we have a viscous drag. So near the walls, the turbulence, the mass motion of the gas mixture have been dampened out, and there is a stagnant body boundary layer, the thin film of the liquid oil which is used there. The large mass of the metal walls also act as a heat sink and conducts away much of the energy being released in the reaction flame. Both of these mechanisms reduce the rate of the reaction and flame speed, and combustion ends by slowly dying away. So both of these mechanisms, the heat sink, the metal walls, and the stagnant boundary layer mechanism reduces the rate of reaction and flame speed, and combustion ends by slowly dying away. Because the rise in the cylinder pressure tapers off slowly towards zero during flame termination, the forces transmitted to the piston also taper off slowly and smooth engine operation results. During the flame termination period, self-ignition will sometimes occur in the end gas in the front of the flame front, and engine knock will occur. The temperature of the unburned gases in front of the flame front continue to rise during the combustion processes, reaching a maximum in the last end gas. The maximum temperature is often above self-ignition temperature. Because the flame front moves slowly at this time, the gases are often not consumed during ignition delay time and self-ignition occur. The resulting knock is usually not objectionable or even noticeable. This is because there is so little unburned air fuel left at this time that self-ignition can only cause very slight pressure pulses. So very slight pressure pulses are there, and this knock is all very less. Maximum power is obtained from the engine when it operates with very slight self-ignition and knock at the end of the combustion process. This occurs when maximum pressure and temperature exist in the combustion chamber, and the knock gives a small pressure boost at the end of the combustion. Now, with this, we have completed the three phases of the combustion: the fuel, the flame ignition and development, the flame propagation, and flame termination, and what's all is happening during all these phases. Now, we have example 7-1. Statement of the example is, we have a spark plug is fired at 18 degree before TDC in an engine running at 1800 RPM. It takes 8 degree instead of 6 degree. The author has given 8 degree of engine rotation to start combustion and get into flame propagation mode. Flame termination occurs at 12 degree after TDC. So we have 18 degree before TDC and 12 degree before after TDC, and it takes 8 degree of the engine rotation. Now the bore diameter is 8.4 centimeter. The spark plug is offset 8 mm. So bore dia is the 8.4 centimeter and spark plug is not in the center. It is 8 mm offset from the center line of the cylinder. The flame front can be approximated as a sphere moving out from the spark plug. So it's a sphere moving out. Calculate the effective flame front speed during the flame propagation. So we have to calculate the effective flame front speed during the flame propagation. Now, Rotational angle during the flame propagation is 10 degree before TDC to 12 degree after TDC. So from where this 10 came, 18, this 18 minus this 8 gives you this 10 degree before TDC. So 12 degree is this one. So 18 minus 8 is 10 degree before TDC during flame propagation. Okay. 8 degrees, your flame is detected ignition and development phase. So, but we are talking about the second phase, the flame propagation. So it starts from 10 degree before TDC and it finishes at 12 degree after TDC. So it makes 22 degree. So time for flame propagation. So degree we know is 22 degree, 360 degree of revolutions we know, and the speed is 1800 RPM converted into 60 into revolutions. So the time which we will get is 0.00204 second. The time for flame propagation is 0.00204 seconds. Maximum flame travel is, no, we have to find the distance. I mean the Dmax is dia of the bore divided by 2, we will find the radius plus the offset, the flame which has to travel from the spark plug. So distance has to which has to be covered. So the dia of the bore divided by 2, the radius, now the offset distance. So distance comes out to be 0.050 meter. Now the effective flame speed, we know the formula. Vf is equal to Dmax by T. So Dmax is 0.050 divided by the time which we have calculated, 0.00204 seconds. So it comes out to be 24.5 meters per second. So the velocity of the effective flame speed is 24.5 meters per second. Now let's see another example. Now engine in the example 7-1 is now run at 3000 RPM. Now the speed has changed from 18 to 3000 RPM. As the speed is increased in the engine, the greater turbulence and swirl increases the flame front speed at a rate such that Vf is equal to 0.85 n. So your velocity of the flame front increases 0.85 n. Flame development after the spark plugs fired still takes 8 degree of engine rotation. So that 8 degrees same there. Calculate how much ignition timing must be advanced such that flame termination again occurs at 12 degree after TDC. So the flame development, the period is 8 degree, that is same, and the flame is termination occurs at 12 degree after TDC. So these only the changes in the RPM and in the flame front speed. So let's find out. Now the flame speed is, we know it's 0.85 into the increased speed divided by the original speed into the time. Okay, so it comes out to be 34.7 meters per second. So with flame travel distance the same, the time from flame propagation is the same. Bore we have 0.050 and offset divided by the Vf 34.5. Now the time required is 0.00144 second. So in that case, the time was when the speed was 1800 RPM. So the time was 0.00204 second. Now the time is again less, 0.00144 seconds. Rotational angle during flame propagation. So let's see the angle. We have the speed converting into seconds, 360-degree revolutions, multiply with the time, 0.0014 seconds. So the angle is 25.92, and whereas previously we have the angle is 22 degree. So the flame propagation starts at 13.92 degree before TDC, and the spark plug is firing at 21.92 before TDC. So ignition timing must be advanced with 3.92 degree. Okay. So we have to advance the ignition timing 3.92 degree. Now, variation in combustion chamber. We have studied the three different phases of the combustion in an SI engine: the flame ignition and development, then the flame propagation, then the flame termination. Now, variation in combustion. Ideally, combustion in every cylinder of an engine would be exactly the same. Ideally, it should be same in all the cylinders of an engine. If we have a 3-cylinder or 4-cylinder or 2-cylinder, the combustion process should be same in all the cylinder ideally. But there would be no cycle to cycle variation in any of one cylinder. But this does not happen due to so many factors, which are due to variations that occurs in the intake system and within the cylinder. Even if no variations occur before combustion, the turbulence within the cylinder would cause statistical variation to occur during the combustion. If we maintain, or we should idealize, that there is no change in the intake system and in the supply system, but within the combustion chamber, the turbulence will be different. So there will be a huge difference in the behavior of the combustion in each cylinder. Now, difference in lengths and geometry of the intake manifolds, that will cause the variation. So the volumetric efficiency will be changed, the air fuel delivered change, different evaporation rate of the gasoline component. So we know that gasoline components have different temperatures at which they evaporate. They have three different temperatures. So there are different composition of molecules. So they have a different evaporation rates of these molecules, different evaporation rates of fuel additives. If we are using some fuel additives, they will be having different evaporation rates. EGR, exhaust gas residue, which are inside trapped inside the combustion chamber. So they will be different for each cylinder. So variation in fuel delivered by the injectors. So how much, although the fuel injectors are phased and calibrated, but this amount of pressure which by which they are delivering, and so many nozzle dia, the amount of liquid fuel which is there. So variation in the fuel delivered by the injector, with all these things, the combustion phenomena in every cylinder will be different. Okay, or in each cylinder it will be different from the previous one. Now, variation: passage of the air around the throttle plates breaks into two flows, causing vortices and other variations that will then affect all downstream flows. Because of imperfect quality control in the manufacturing of fuel injector, each injector does not deliver the exact same quantity of the fuel, and there will be a cycle to cycle variation from any one injector. The standard deviation of air fuel within a cylinder is typically on the order of 2 to 6% of the average. So, as we know, there is mechanical tolerances in every equipment. So due to those, the injectors quality, manufacturing quality, there is a 2 to 6% of average. There is a standard deviation in the air fuel ratio. Now, typical variation of air-fuel ratio, which may be delivered to a single cylinder in 30 consecutive engine cycle. So now we have a single cylinder in which we take 30 consecutive cycles. Means if this is an SI engine, means 720 degree multiplied by 30. This is the number of cycles. So air fuel ratio from 15 to 19, we have the range. This is the average we take somewhere here. So in every cycle, first cycle, second cycle, third cycle, fourth cycle, fifth cycle, and 13th cycle, there will be variation in the combustion. Okay. Now, let's see the time versus cylinder pressure. Pressure as a function of time for 10 consecutive cycles in a single cylinder of an SI engine. 10 consecutive cycles means 10 into 720 degree. So this comes to be 10 cycles. Okay, one cycle is of 720 degree in SI engine. Remember this thing. So you get the ignition here. So there are in every cycle, the maximum pressure will be different. If you replace this pressure here, temperature, so temperature will be different here. Now, Sicilian photographs of the start of the combustion for two different cycles in the same test engine cylinder using propane fuel at 1400 rpm and a spark plug gap of 0.8 mm. Variations results from randomness of a cylinder turbulence and a cycle-to-cycle on inconsistencies in swirl, squish, and tumble. Once there is a variation at the start of the combustion, the entire combustion process will be different for the two cycles. So if there is a variation, there will be a if in the start of the combustion cycle we have a variation, then we have a same will continue throughout the cycle. Now combustion in divided chamber engine and stratified charge engine. Now we have studied this diagram in our chapter 6. We have two chambers here. One is secondary, one is main. In main, this constitutes the 80% of the clearance volume and this 20% of the clearance volume, as we have studied. Now, combustion in divided chamber engine and stratified charge engine. Let's see. Combustion chamber divided into main chamber and a smaller secondary chamber to create different intake and combustion characteristics in the two chambers. The volume of the small secondary chamber is typically up to about 20% of the total clearance volume with objectives. High swirl and jet ignition or torch ignition in stratified charge engine do not have a homogeneous air-fuel mixture throughout the combustion chamber, rich mixture around the spark plug and leaner mixture away from the plug. So the combustion properties will be different. Some engines have one intake valve in the main chamber and one in the secondary chamber of the each cylinder supplying fuel at different air-fuel ratio. So due to intake valve's position, we have different air-fuel ratio. A variation of stratified charge engine are dual fuel engines. These engines use two types of fuel simultaneously, one usually a cheap fuel and a lesser amount of a better fuel used to assure ignition. So we have this divided combustion chamber and then we have a stratified charge engine. So in every type geometry, the combustion properties will change. Now, divided combustion chamber of a CA engine with fuel injector mounted in secondary chamber. So this is your valve, this is your injector. And here, if we have the valve here and the injector here, and this is the piston, so this is like this. Schematic of a combustion chamber with passive secondary air chamber was found on some SI and CA engines. During the high pressure of a combustion gas, air-fuel air fuel and or exhaust is forced through a small orifice and fills the secondary chamber. This is your secondary chamber. Then as cylinder pressure is reduced during the expansion stroke, the gas in the secondary chamber slowly flows back into the main chamber, slightly extending combustion and power stroke process. So this comes back to this and you extend the combustion chamber. So with this, we comes to the first part of our lecture of this chapter 7, the combustion. Now, thank you very much for